Hi, this is Unit 4, Day 10. In this video, we're going to cover both Part 2 and Part 3 of our exploration. So let's start with some background knowledge. In Part 2, we're going to look at comparing polar molecules versus polar bonds. So let's take a look at the molecules that have electrostatic maps. Now remember, these maps are color code the surface of the molecule. And if it's red, that means that part of the molecule is negative, and if it's blue, that means that part of the molecule is positive. Also, we know that polar molecules would have a positive and negative end. So it should have a red end and a blue end. So looking at these molecules here, which of these molecules do you think is or are polar? All right, so let's take a look at this, starting with NH3, ammonia. So in this case, this is polar. It has one end is positive, blue, and the other end is negative, red. And we can sort of use the partial positive and negative symbols to sort of show that. So where the nitrogen is, that's negative, and then where the hydrogens are, that's positive. Let's take a look at CO2. CO2 is actually nonpolar, and that's because both ends are negative. Now, when I say ends of the molecule, you may be thinking, well, what about where carbon is? That's in the middle. That's not on the ends. So you need to have an end that's positive, so an end that's blue, and then an end that's negative, and an end that's red. Both ends are negative, so in that case, this is a nonpolar molecule. The last one we're going to look at is CH2O, which is this is formaldehyde. And taking a look at this one is polar. You have a negative end where the oxygen is and positive end where the hydrogens are. Now, in addition to looking at electrostatic potential maps, we can also represent the polarity of these molecules using the molecular dipole. Now, remember, the molecular dipole is not a bond dipole. The bond dipole is for an individual bond, but a molecular dipole points to the negative side of the entire molecule. So, for example, in NH3, the bond dipole would point up towards the nitrogen. CO2 is nonpolar, so it would not have a molecular dipole. CH2O, it would point towards which atom? Great, the oxygen, because that's where the negative side is. Okay, so in this simulation, what we're going to do is we are going to learn the difference between a polar bond and a polar molecule. And we're going to look at a molecule like this one. There are 3 atoms with a total of 2 bonds. And we're going to see how a molecule can have a polar bond, but be a nonpolar molecule. So let's go ahead and go to the Phet link. If you're doing this along with me, you might want to pause and then go to that link. And we're going to click on the 3 atoms because that's the one we're looking at. Now, when you get there, you probably see something that looks like this. We're going to, first off, notice that some of them have different electronegativities. We're going to change that in a moment, but I want you to notice how there are 2 dipole arrows. The black is for the individual bond. So, for example, if I click on that, I can show the BC bond here. The bond dipole is pointing to boron because it's more electronegative than C. And similarly for the AB bond, it points to B because it's more electronegative. And that's for the individual bonds. So the black one's for the individual bonds. That's why we have 2 of them. But the one for the entire molecule will be this orange-yellow kind of color. All right. Now I want to change a couple of things. I actually want them all to have the same electronegativity. And notice when I do that, the molecular dipole goes away because there's no difference in electronegativities anywhere. So they're sharing electrons equally. So the molecule is nonpolar. The other thing I want to do is I want to make it linear. And to do that, you just click on the atom and you just drag it up. So I'm just going to drag that up. And now we have a linear molecule. Okay. All right. So we have a linear molecule and it's nonpolar because they all have the same electronegativity. Now what I'm going to have you do is I'm going to have you take atom C and I want you to gradually ramp up its electronegativity. All right. So what do you think will happen to the molecular dipole? Will the molecule become polar and get a molecular dipole? Or will it remain nonpolar if you increase the electronegativity of atom C? All right, so let's take a look what happens. I'm gradually increasing it. And notice how the molecular dipole is pointing towards atom C. This is the most electronegative atom, so it's going to pull the electrons toward it. All right, so now we have a polar molecule because it has a molecular dipole. It's pointing on that side. Now, let's go ahead and check out the bond dipole. where do you think you'll have a polar bond? AB or BC? Take a look at the electronegativities. Great, so if we go ahead and click on that, notice the only polar bond there is the BC bond, and that's because those are the, there's a difference in electronegativity between B and C. However, the atoms A and B have the same electronegativity, so this will be a nonpolar bond. All right, let's go ahead now and make atom A as electronegative as atom C. We're going to do that gradually. We're going to gradually increase the electronegativity of atom A. What do you think is going to happen to, one, the dipole, the bond dipole, the black arrow? Will we get a bond dipole here? And what do you think is going to happen to the molecular dipole? Will it change or stay the same? All right, let's go ahead and check that out. Let's see. So I'm going to gradually increase the electronegativity. Notice that all of a sudden I'm getting a bond dipole because this bond is becoming more polar. A is more electronegative, so the black arrow or the bond dipole point towards A. And I want you to also take a look at what's happening to the molecular dipole. So now focus on that. Notice how it's getting smaller. Now we're about halfway there, so it's about half the size that it originally was, right? Why do you think that is? Well, remember, atom A is becoming more electronegative now, so it's pulling the electrons toward it. C was the most electronegative, was the strongest, but now it's got a little bit of competition here, so it's not getting as much electron density, or the electrons aren't being pulled as close towards C because it's got a little competition from A. Let's go ahead and ramp it up all the way up to the same as atom C. Look what happens to the molecular dipole. So is this molecule polar or nonpolar? That's right, it's nonpolar. And we know it's nonpolar because there's no molecular dipole. But the strange thing is it has two polar bonds. Both bonds A and B are polar, and B and C is a polar bond. So this shows you that you can have a molecule that has polar bonds in it, but the overall molecule is nonpolar. So why is that? It's because that these bond dipoles cancel each other out. Think of atom A and C as being these equally strong twins, and they're both pulling on B. Well, if they're equally strong, no one's going to win out, right? So the electrons aren't going to go just to one side of the molecule, right? So let's go ahead and go back to some of the key takeaways here. So when we're talking about a polar bond, that's an individual bond with a partial positive and partial negative atom. But in the case of a molecule, when we talk about a molecule has a positive and negative end of the entire molecule, not just a single atom. So you can have a molecule like CO2 that has polar bonds, but will be a nonpolar molecule because the bond dipoles cancel out, right? So that's why if you look at something like CO2, which is shown here in the electrostatic potential map, or here, those bond dipoles cancel out. This is a nonpolar molecule. All right, the last thing we're going to do is dive right into part 3, where we're going to compare talk about the shapes. So in this part of the simulation, that's to say part 3, by the way, we're going to learn the importance of shapes in determining if a molecule is polar or nonpolar. And we're going to look again at the same molecule with 3 atoms. So we're going to change the shape from this linear shape to this sort of bent or angular shape and see what happens. So let's go right back to our simulation. All right, so I'm not even going to change it out. All I'm going to do is I'm going to add the partial charges just so we can see that where they are. And what I'm going to do is I'm going to turn this back to the shape that it was. Remember how when we started it was bent or angular? So to do that, all I got to do is just drag down the atoms. Notice what's happening here. I'm getting a molecular dipole. What does that tell me? Is this molecule polar or nonpolar now? It's a polar molecule. So let's go ahead and bend down the other atom. Okay. So when this molecule is bent, it's actually a polar molecule. Now, why is that? When it was linear, the bond dipoles were able to cancel each other out. They were pulling equally against each other, so they canceled out. But do they cancel out in this case if they're both pulling downward? Nope, they don't. Okay, so they're both pulling in the overall down direction, right? So as a result, the bottom half of this molecule, where A and C are, will be negative, right? And the top half where B is will be positive. All right, if you want, you can go ahead and play around with this some more and changing electronegativities of atoms and seeing what happens as you do that sort of thing. So you're welcome to do all that. But going back to sort of some key takeaways from part 3. So the main thing is with part 3 is that the shape of the molecule also determines if it's polar or nonpolar. So if you have a linear molecule like CO2 where the bond dipoles cancel out, the over molecule is nonpolar. But if you have a bent molecule like water is actually a bent molecule, then the molecule is polar. Now you may be asking, well, I can see that in a linear molecule, the bond dipoles cancel out. And in a bent molecule like H2O, they don't. So the overall molecule is polar. But how can I tell the shapes? Well, that actually comes from what's called the VSEPR, or valence shell electron pair repulsion theory. So that's a sort of a different topic. But for now, what you need to know is that shapes also determine if a molecule is polar or nonpolar. That's it for this lesson. Have a quality day.